Have you ever really stopped to think about what connects, say, the chair you're sitting on to the air you're breathing? Well, today, that's exactly what we're going to do. We're diving deep into the architecture of matter itself, starting with the tiniest little pieces and building all the way up to the materials that literally shape our world.
All right, so let's kick things off with a simple question. You've got a block of ice, a puddle of water, and the steam rising from a kettle. They seem totally different, right? A solid, a liquid, a gas. But what's the one thing that truly connects all three?
And the answer is, they're all made of the exact same stuff. We're talking about tiny, tiny particles that are just constantly in motion. The only real difference between that ice, water, and steam is how much energy those little particles have, and how much freedom they have to just zip around.
You know, you've seen proof of this your whole life. Think about stirring salt into water. It looks like it just vanishes, right? But what's really happening is that the tiny salt particles are slotting themselves into the empty spaces between the water particles. It's a great reminder that even something that looks solid, like water, is actually mostly empty space.
Okay, so this brings us to a really, really big question. If everything is just a bunch of separate particles whizzing around, what stops the whole universe from just, flying apart? What's holding it all together?
Well, the answer is the chemical bond. And honestly, the best way to think about it is as the fundamental glue of the entire universe. It's this attractive force that grabs onto individual atoms and holds them together to make molecules, and molecules make up, well, everything.
Now, one of the most important types of this glue is the covalent bond. And its whole deal is sharing. See, atoms can share one pair of electrons, which we call a single bond. Or they can share two pairs for a double bond. And they can even share three pairs, forming a really powerful triple bond.
And check out this table, because it tells a really cool story. Notice how, as we go from a single to a double to a triple bond, the length gets shorter and shorter. The atoms are literally pulling closer together. And as they get closer, the bond gets way, way stronger. It's kind of like the difference between a casual handshake, linking arms, and a full-on superglue connection.
So now that we understand the glue, let's see how it actually builds things. And to do that, we need to introduce the absolute superstar of our story, the element carbon. Carbon is just special. It's a molecular rock star for a few key reasons. First, it can form 4 incredibly stable bonds at the same time. It's also uniquely good at bonding with itself, creating these long, stable chains and even rings. And it can pull off all 3 types of covalent bonds we just talked about. All of this makes it the perfect backbone for a massive family of molecules we call hydrocarbons.
The first branch of this carbon family is the alkanes. These are the simplest of the bunch. They only have single carbon-carbon bonds. This makes them what we call saturated, and they're very stable. That stability is exactly why we find them in reliable fuels like the propane for your grill or the butane inside a lighter.
Next up, you've got the alkenes. Now, their defining feature is that they have at least one double carbon-carbon bond. And that double bond, it's like a little hot spot of reactivity. It makes these molecules unsaturated and just perfect for being a building block for other, bigger things, most famously, plastics.
And finally, we have the alkynes, which rock at least one triple bond. Now that triple bond packs a serious punch. It's got a ton of energy, which makes these guys highly reactive. The most famous example is probably acetylene gas, which is the stuff that gets mixed with oxygen to create those incredibly hot flames in welding torches.
Okay, so now that you're an expert on these bonds, let's tackle one of the great puzzles in the history of chemistry. Let's talk about the mystery of a molecule called benzene.
So here was the problem. Benzene's chemical formula is C6H6. Now, based on everything chemists knew about bonds, that formula screamed that it should be packed with double or triple bonds, meaning it should be super reactive, just like an alkene or alkyne. But when they actually ran the experiments, benzene was shockingly stable. It was almost blazy. It just didn't add up.
The big breakthrough came from a chemist named August Kekulé, and the story is legendary. He had been wrestling with this problem forever. And then, one night, he had a dream. He dreamt of atoms dancing and twisting around like snakes. And then suddenly, one of the snakes grabbed its own tail and started spinning in a ring. He woke up in a flash. That was it! Benzene wasn't a chain, it was a ring.
But, even that ring structure wasn't the full picture. The real secret sauce to benzene's stability is a concept called resonance. The easiest way to think of it is that the molecule doesn't have fixed single and double bonds that switch back and forth. Instead, those extra electrons are shared equally all the way around the entire ring, creating the super stable hybrid structure. It's this shared cloud of electrons that makes it so incredibly unreactive.
So we've gone from particles to bonds to the amazing families of molecules carbon can create. For our final section, let's see how we actually harness that carbon superpower to build the materials of the modern world.
The key process here has a fancy name, polymerization, but the idea is actually super simple. You take a whole bunch of small, individual molecules, we call those monomers, and you link them all together to form these incredibly long chains, which we call polymers. Seriously, the best analogy is just taking a huge pile of single Lego bricks and snapping them together one after another to build one long chain.
So let's see how this works to make a plastic that's everywhere, polythene. You start with a gas called ethene. That's an alkene, remember, with that reactive double bond. You add some high temperature and pressure, and that reactive double bond basically pops open. This allows all the individual ethene monomers to link up, end to end, forming the massive polymer chain we all know as polythene.
And that simple process is nothing short of revolutionary. It's how we turn a simple gas into, well, everything. From the plastic in a shopping bag or a milk jug to the super advanced materials used in medicine and aerospace, it all comes back to knowing how to control that chemical bond.
So, there you have it. From simple particles to complex polymers, this elegant architecture is what underpins our entire world. Carbon gives us the fuels that power our society and the plastics that shape it. But let's not forget, it is also the backbone of life itself. It's in every protein, every fat, every carbohydrate in your body. It really makes you wonder, doesn't it? What other secrets are still hidden away in these simple bonds?